Welcome to Week 1, Chapter 1.5, Part 1 of 14, Hypothesis Testing Done Right. Sam has a trading rule. Each morning, buy yesterday's biggest losers, hold one day, sell at the close, betting they bounce back. Over 252 trading days, the rule earned an average of 8 basis points a day, which annualizes to more than 20%. Sam is briefly very excited. Then the right doubt arrives. The daily returns bounced all over the place. Could a rule whose true edge is exactly 0 still produce a positive sample average just by luck? That single question, could pure luck have produced what I'm seeing, is the engine of this whole chapter. In this opening part, we write down the two competing claims a test pits against each other. A hypothesis test starts by writing down two competing claims, not about your sample, but about the population or process that generated it. The null hypothesis, written H0, is the claim of nothing going on. It is the skeptic's position, the boring default you believe, until the data force you off it. For Sam, the population quantity of interest is the true expected daily return of the rule, mu, the average it would earn over an infinite number of days under the same conditions. The skeptic says the rule has no edge. H0 says mu equals 0. The alternative hypothesis, written H1, is what you suspect might be true instead. Sam suspects the rule makes money, so H1 says mu is greater than 0. Why pick 0 as the null rather than some small positive number? Because 0 is the value that means worthless, the dividing line between an edge and an anti-edge, and the thing a skeptic believes at no cost. The null is generally the uninteresting status quo value, the one whose rejection would count as a discovery. Choosing it well is a scientific judgment, not a statistical one. Three things deserve emphasis right away, because this is where the logic lives. First, the hypotheses are statements about mu, the unobservable population mean, not about x bar, the sample average Sam actually computed. We know x bar equals 8 basis points with certainty. There is nothing to test about a number we already hold. The whole exercise is about what x bar lets us infer about mu. Second, the test is deliberately asymmetric. We do not treat the null and the alternative as two equally matched contestants. We grant the null the benefit of the doubt and ask whether the data can overturn it, the way a courtroom presumes innocence, and ask the prosecution to overcome that presumption. This asymmetry is a choice, and it is the reason a test's conclusions are phrased so carefully. Third, the null is almost always a single point, like mu equals 0, precisely because a point gives us something concrete to compute with. If we assume mu equals 0 is exactly true, we can ask exactly how surprising Sam's 8 basis points would be. We could never do that with a vague, the rule is bad. To summarize part 1, a hypothesis test pits a null hypothesis against an alternative. The null, H0, is the skeptic's boring default. For Sam, mu equals 0, the rule has no edge. The alternative, H1, is what you suspect, mu greater than 0. Both are claims about the unobservable population mean mu, never about the sample average we already hold. The null gets the benefit of the doubt, like a presumption of innocence, and we make it a single point so we have something concrete to compute with. In part 2, we take Sam's 8 basis points and the noise around them and crush them into a single ruler, the test statistic.